Hey there, and welcome back to The Explainer. Today we're tackling something seriously cool. We are taking Chapter 17 from the Cambridge A-Level Physics syllabus, Oscillations, and we're going to transform it from, a dry list of equations into a deeply fascinating roadmap of how the universe actually moves. If you're studying this syllabus, or honestly, even if you just want a distraction-free grasp on the raw mechanics of motion, you are absolutely in the right place. So let's just jump right in.
Okay, quick question for you. Think about this for a second. What do the swinging pendulum of a grandfather clock, the bumpy up and down of your car's suspension system, and the invisible vibration of a single atom in a crystal lattice, what do they all have in common? On the surface, literally nothing. But in the world of physics, they are governed by the exact same set of rules. They're all experiencing oscillations. And honestly, oscillations dictate the mechanics of our entire physical world, from the massive, macro level all the way down to the quantum scale. It's kind of mind-blowing.
Here is our roadmap for today's explainer. First, the rhythm of physics. 2, simple harmonic motion explained. 3, the energy interchange. 4, damping, slowing things down. And finally, number 5, the power of resonance.
Part 1, the rhythm of physics, where we'll be understanding the basic vocabulary of movement. Let's get right into it.
Well, you really can't understand the poetry of physics until you know the words, right? So let's start with a classic visual, the Newton's cradle. You've probably played with one of these before. You lift up one of those shiny silver spheres, you let it drop, and you don't just get that satisfying clack-clack sound. You're actually observing rhythmic, periodic motion. It's motion that repeats itself over a specific, totally predictable period of time. Our goal here is to take that intuitive visual and apply the exact language the syllabus requires to describe what's happening at literally every millisecond of that swing.
To pull that off, the Cambridge syllabus wants you to master 6 core terms. Let's quickly demystify them because it's actually pretty straightforward. First, displacement. That's just how far our object is from its resting center point, right at this exact moment. Next is amplitude, which is the maximum possible displacement, basically the absolute peak of the swing. Then we have the period, the time it takes to complete one full back-and-forth cycle. Frequency builds right on that. It's just how many of those cycles happen in a single second. Now, angular frequency sounds scary, but it's really just a mathematical trick linking frequency to circular motion using pi. It makes our formulas way cleaner later on. And lastly, phase difference, which tells us how out of sync two oscillating objects are with one another. Boom! Those 6 terms? That's your absolute toolkit.
Section 2, simple harmonic motion explained, the idealized world of perfect swings.
All right, now that we have the vocabulary down, let's step into the core rulebook of oscillations. We're entering this theoretical, perfectly frictionless world of what physicists call simple harmonic motion, or SHM. Now, the definition of SHM is arguably the most critical concept in the whole chapter. It occurs when an object's acceleration is directly proportional to its displacement from a fixed point, and, this is absolutely crucial, it acts in the opposite direction. I really want you to visualize this opposite direction bit like a rubber band. Imagine an object attached to a rubber band. The further you pull it away from the center, so the greater the displacement, the harder that rubber band snaps back. It's this stubborn, rebellious, restoring force that is always pulling the object back to the center line.
And you know what's really interesting? The actual data sheet you're going to get in your exam literally hands you the answer. The crucial formula for simple harmonic motion, acceleration equals negative omega squared x, is just a mathematical translation of our rubber band metaphor. The x is the displacement, the omega squared is our proportional constant, and that vital negative sign right there at the front, that represents the restoring nature of the force. It's mathematical proof that the acceleration is always opposite to the direction the object was pushed. I know it looks a little intimidating at first glance, but it's just telling you a very logical story about a rubber band.
Section 3, the energy interchange, the hidden mechanics driving the motion.
Okay, let's keep building on this. We know how to describe the swing itself, but what is secretly fueling it? Let's peel back the visible motion to reveal the invisible exchange of energy happening right beneath the surface. The syllabus specifically demands you understand the total energy of an oscillating system. In our ideal frictionless world, that total energy stays perfectly constant. The equation is total energy equals 1/2 times mass times angular frequency squared times the amplitude squared. Since none of those variables change during a single uninterrupted swing, the total energy is completely locked in. But wait, if the total energy doesn't change, what actually makes the thing move?
Well, the secret is a constant, perfect trade-off between two forms of energy. Think about it. At maximum displacement, the absolute top of the swing where the object pauses for just a tiny fraction of a second before falling back, its kinetic energy is totally zero. every drop of the total energy is stored as potential energy. But as it snaps back to the exact center point, zero displacement, our imaginary rubber band is totally relaxed. So, potential energy is zero. All of that energy has magically transformed into kinetic energy, which is exactly why the object is moving at its absolute maximum speed right through the center. They just constantly trade places back and forth, but their sum, it always perfectly equals the total energy.
Section 4. Damping. Slowing things down. This is where friction enters the chat.
Obviously, we don't actually live in an ideal frictionless vacuum. So it's time to bring reality back into the picture and introduce resistive forces. Physicists call this damping. Depending on the environment, an oscillating system is going to experience one of three types of damping. Let's step through them so you can vividly picture the physics happening. Number one is light damping. Just think of a normal pendulum swinging in the air. The amplitude gradually decays over many swings until it finally stops. Number two, critical damping. Now this is engineered perfection. Think of your car's suspension hitting a nasty speed bump. You want that car to return to its flat resting position incredibly fast without bouncing up and down, right? That's critical damping, the fastest possible direct return to zero displacement. And finally, number three, heavy damping. Picture swinging that exact same pendulum, but this time it's submerged in a vat of thick mud. It's just going to slowly, sluggishly creep back to the center without ever actually swinging past it. Section 5. The power of resonance, when external forces match natural frequencies. So, here is the crucial question. What happens when we don't just slow systems down, but actually force them to move by applying our own energy? This brings us to the grand finale of Chapter 17, Resonance. Every single object has a natural frequency, basically the rate at which it wants to oscillate if you just strike it and let it ring. Resonance happens when we force a system to oscillate by applying an external push, and the timing of that push perfectly matches the object's natural frequency. When those two frequencies lock in, wow, you achieve an astonishing maximum transfer of energy resulting in the maximum possible amplitude. It's exactly like pushing a kid on a playground swing. If you push at the exact right moment of their natural swing cycle, they go higher and higher and higher.
And hey, this isn't just theory. This is immense world-shaping power. Resonance is the exact reason a trained opera singer can literally shatter a crystal glass with just their voice. They are perfectly matching its natural frequency. But it's also the precise mechanism we use to keep perfect time in the ports watch on your wrist. From simple rhythmic swings to the dramatic, powerful transfer of energy, oscillations are essentially the heartbeat of the physical universe. So now that you understand the mechanics, the vocabulary, and the math behind it all, the real question is, how will you apply and control it? Thank you so much for hanging out with me for this incredibly focused explainer. Keep reviewing these concepts, trust the process, and I will see you in the next breakdown.